Okay, let's see, how delayed are we? Hard to say. All right, let's begin. Where am I right now? Yes, here we go. So the first thing is, after class, am I available for a question about the project? Sure. Second thing, let's begin. So where did we leave off last time? The answer was we were writing a mega simple AVL, simple AVL insertion. Basically, we were just doing AVL insertion, okay? And so, and then what we're going to do today is we'll talk about red-black insertion, okay? So we'll do these two things, and I think that will be good. I'll explain what red-black trees are in just a bit, but so remember where we were in the AVL tree insertion. Let's actually just look at the code. We were doing some live coding, and here it is. Basically what we were doing here is we were writing this insert helper, right? Where what we do is we set the m root is equal to the insert helper, and we stick in the value, and then here we call insert helper on wherever we currently are, and then we go down and we do all this stuff. So what do I mean by do all this stuff? I guess I should say that we have to refresh the heights before we do anything, because if we don't refresh the heights, we won't know if there's an imbalance. I guess an imbalance now, right? And then what we have to do is rebalance, maybe, right? And then we refresh the heights again, and this just ensures that the heights are correct again. And then probably we'll have to return something. Here we return p current. We might have to do something where we set p current equals to rebalance. But anyway, this is basically how AVL insertion should work. So let's go and, and of course this is just part of it. Let's check, have I done the refresh heights? Remember how refresh heights worked? You check if it has a left and it has a right. If it has both, then you set, remember that the height, the definition of height is height of a node is equal to 1 plus the maximum of the height of the node dot left, and and the height of node right. And I guess I should use the same notation both times, so I'll use the arrow notation. So this is the definition of the height of a node, and this is basically the way that you have to compute it. Unfortunately, basically all of this is just edge case, right? Like, you would love to be able to just do this in one line, and you could kind of do it in one line, but it's better to just write it out like this. Okay, so that's that, and then remember here, this is supposed to rebalance, and so what do we have to do, right? And so what we have to do is we have to detect, basically we have to detect the type of imbalance, right? And we have to detect whether it's like a left-left, left-right, right-left, or right-right imbalance, right? Or correct. And then what we have to do is we have to fix it, right? So let's do that, right? So how do we do that? Basically, we can detect if something is left-heavy by saying if the p subroot dot, what is it? Height? Yes. Or p subroot dot p left dot height is bigger than p subroot dot p right dot height, right? Almost, right? But because you're allowed to differ by more than one, so if the left height is bigger than the right height plus 1, right? Then basically what that's saying is that if you subtract the right height from the other side, that left height minus right height is bigger than 1. So this is a violation. So this means we're left heavy. And then we do else if, and then we can basically copy paste this condition and just change left to right and right to left. P right. Nope, I just change it back to the same thing. P left, P right. And so now this means we're right heavy. And so basically, otherwise, do nothing, right? Because if you're not left imbalanced or right imbalanced at the current node that you're at, at the current node where you are, I was about to say at the current node where you're at the current node where you're at. No. So, okay, so basically here we've detected left heaviness and right heaviness. You know, and so this tells us whether or not the tree is heavy to the left or heavy to the right by enough that we have to rebalance it. So what are the two cases now? The two cases are, well, if it's left-left, then basically and of course, this code is not going to quite work because you might ask the completely valid question, what if P left or P right don't exist, etc. Will that cause problems? And the answer is yes, it will. You know, seg faults will happen. So we're going to have to modify this code and add in a bunch of edge cases. But otherwise, let's just keep going. So let's assume that we're in a case that's not an edge case. So we say P subroot dot P left right dot height is bigger than or equal to P subroot dot P left dot P right dot height. Now, of course, here let me promise you that, or let me tell you that if this code doesn't scare you, then you're very brave. And the reason why this code should scare you, right, is because you're doing a P left dot P right. The thing is, you might know that subroot exists. Like, subroot is always going to exist, I think, if the insert function works correctly. But you don't necessarily know if it has a P left. And if it has a P left, you don't necessarily know if it has a P left on the P left. And if it does, you don't necessarily know that it has a height, right? You don't necessarily know these things. And that's the problem. You don't. So it's possible that this just doesn't exist. And that could be an issue, right? So we'll fix all that up in just a bit. And then here, we know that there's an imbalance, so really all we have to do is just an else, right? So this here is the left-left case, and this is the a left-right case. Why is it unhappy with me now? What have I done? If statement has identical branches. I don't care. It's just yelling at me because I haven't put any code in there yet. So now let's do the same thing. So except now we have to do P right here, and here we'll do P right. And so this is the right left case and the right right case. And so basically, what are we going to do in all of these cases? What we're going to do is well, let's not even worry about this yet. Let's worry about this part here, right? So what do you do if you have a left-left imbalance? You know? And the answer is, whenever you have a left-left imbalance, you rotate right, okay? And you rotate right on, you bring the subroot dot left up to the root, or a subroot, I should say. Right, so that's how you do it, is you bring the subroot up. So I think for our rotations, now this is a decision you have to make, though I think that in this project, since we don't have parents, you always have to rotate on the parent node. You have a choice, right? Your choice is to rotate on the parent or on the child, but we don't have parents in the project, So rotate on the parent, right? Because otherwise you won't be able to actually do everything you need to do. So, okay, so this, we're just going to rotate on the parent. So we'll call, what is it called? Rotate right. Yep, rotate right. Rotate right, and we'll just call it on P subroot. And that's it. And then maybe just for the sake of safety, we'll return it. That'll make us happy, right? We'll make it return an AVL tree node pointer. And so what that's going to do for us is it's going to make sure that, and I'll show you what we're about to do with this. So when we call rebalance, let's see, when we call rebalance, what we'll do is we'll set P current equals to rebalance P current, and then that way it'll fix up, because remember the P current is going to point to, now it's going to be shifted over to the right or something, and so it's not going to be the same node anymore, so you want to make sure that this is fixed. Okay, so let's keep going. So that's it. You return rotate right. Now for the other case, what do? Right? For the left-right case, remember you have to rotate left. The first thing is you rotate left on the, let me draw out this case for you. So this is this case, right? Man. One time I made a Pac-Man, and now it always wants to make Pac-Man. Okay. Oh well, okay. So basically we're talking about this condition, right? The unbalanced condition where this is the left-right unbalanced condition. And so if this is like A, B, and C, then what we do first, if you remember, is we rotate B down, C up, and we end up with this structure. And remember that the reason that we do this is to make, right, the reason why we do this is to make the left-left condition again, right? So that's why we do this, and then we rotate this as if it was a left-left imbalance, because now it is actually a left-left imbalance. So then we rotate this, and then we get this. The main concern here, so there's two concerns when you do this. First, you have to link up all the pointers correctly. The second concern is that we have to return C now, because at least to the higher levels of the tree. And the reason why we have to do that is because the higher levels, right, let's say that this isn't the root of the tree, this is just like some point in the tree, there's some nodes above this, right? So there's some node here, like, I really wish I could get rid of that. There is I mean, I have been able to do it. Okay. Nope. All right, whatever. So there are nodes above this, so it could the thing is that this could either be a left child or it could be a right child. You don't even know. So technically this could be over here, or technically the node could actually be on the other side. And you just don't know where the parent is. But the point is that the parent has to be told that now it's not pointing to A anymore, it's pointing to C, right? So that's the thing. If the parent of all of this needs to be, told that it's pointing to C now, right, rather than A. Okay, so let's go back and do this thing. So we're going to rotate, let me see. Yeah, we're going to rotate left on the P subroot dot left, and let's do that. So we'll say rotate left, let's say P subroot dot P left is equal to rotate left on P subroot dot P left. There we go. And then finally, let's just say return and rotate right on P subroot. And so remember that this is going to rotate it's going to rotate the right child of P left up. And so that's what this is going to do. It's going to rotate the right child of P left up. And then this is going to rotate the left child of P subroot up. And then what we do is we just return the rotate right. And the reason why we're doing that is so that we'll at least pass the new root back to the original function, and then we'll do some stuff. Now, the whole point about all this is now these are all symmetric cases. So here, all we have to do is return rotate left on P subroot. Cool, right? And the only reason why I have to do that is, oh wait, I'm sorry. This is the right case. So this is the symmetric to the left case, right? And so now this case is symmetric to the middle case here. So basically what we have to do is we have to do this. We have to say P right is rotate right on P right, and then we have to rotate left. I think that's right. Oh God, I shouldn't say right. I think that's correct. So I think that gets us where we're going. It could be totally wrong because, you know, I've just done some silly stuff. So, okay. Now, the last thing that we have to do before we fix up all these null pointer problems that we're going to end up with, and I wish that this function could be this simple, right? Because if you delete all the comments, this is actually a really short little function here. Okay, let's do rotate right. So let's actually do it and think about it. So let's think about how rotation works, and then let's do the rotations. So how does rotation work, right? Now I really want to, let's see, is it going to disappear? There we go. Perfect. Okay. I think I've convinced it to stop doing that. All right, so okay. So the point here is that what we're going to do is, let's look at this thing. We're going to rotate. Which one am I going to do first? I'm going to do rotate right first. There's no real preference, but I just wanted to see which one I was going to do. So if we rotate right, that means that we're going to rotate in this direction. So we're going to rotate like this, right? We're going to rotate this way. And so this node is here, this node is here, and all of these have their own little children. 5. Let's make that 3. Okay. All of them have their little subtrees. Let me draw in their subtrees. And now we don't mess with everything, right? But I'm going to draw everything in just so that we have everything drawn in, and then we will connect everything, and then let us actually do the rotation, and then we will talk about how to actually do the coding. So I'm going to call this, I'll call this left, I'll call this node, and I'll call this right. You know, not terribly surprising. And this will be left, right? You know, this will be left, right. Let's do right, left. And finally, right. So, okay. So how do we do the rotation? What we know that we have to do on the rotation is that, I guess I should put the arrow on. But in order to do the rotation, right, what we're going to do is we are going to take this node, the left node, and move it up to the node, and we're going to push this one down. So as it turns out, these two don't actually play any part in the right rotation. So for right rotation, these subtrees don't really do anything. So let me just move all of this out of the way just a little bit, push it down here, and then I'm going to push this node down here, and we're going to push left up to the root. right? So this is what we do. And so what are the things that we have to do, right? So this is how the tree is going to look. And let me just connect these in a kind of stupid way. And then, of course, here, what we have to do is you have to prune this part off and join it on over here. And, of course, this looks more imbalanced, but the reason why it looks more imbalanced is because we just don't have these like proportionally sized or anything. So, you know, if we're going to do a right rotation, so I think this is good enough, right? So this will tell us everything that we need to do, or almost everything that we need to do. Right, so what we need to do is we need to set node.left is equal to left.right, and we have to say that left.right is equal to node. Right, now these two statements, there's no real way to do this, right? They will conflict with each other regardless of the order that you put them in, you know? So what you actually need is some kind of temp is equal to, say, node, right? And then, or maybe temp is equal to left.right, and then what you do is you say left.right, blah blah blah, and then that's equal to temp. But that's just actual, that, you know, that's coding business. But the point is, like, you notice that those two lines of code do interfere with each other because there's no, I don't think there's a good way to like order them so that you're not messing stuff up. So then this is how you do it, and that's all you really have to do. And then the last thing you have to do is basically return left, or somehow set left's parent's child to, or I'm sorry, node.parent.child equal to left. Now the thing is that in our project we don't actually have a parent pointer, so that's why I'm not kind of doing it this way. But this is also a valid way to do it. The way I'm doing it in this example is just returning the value. So let me show you what I mean by that. So okay, so let's do the rotation. Let me remember what I have to do. To rotate right, I have to set, okay, let me actually just copy paste this into a comment so that I don't forget what I need to do. Okay, so this is what I need, and let's do it. So let's say well, let's just do auto because I'm lazy. Temp equals p subroot dot left, p left dot p right. There we go. And then left. Let's see, p subroot dot p. Well, let's make another auto. I don't think we have to do that yet. No, we're good here. So we can do p subroot dot p left dot p right is equal to p subroot, right? Because that's what the node is. And then finally we do p subroot dot p left is now equal to the temp, and then we return not the p subroot, right? No, right? Because who is the, well, actually, who is the new root, right? Who's the new root? So p subroot, okay, who's the new subroot? So p subroot dot left dot right is equal to the subroot itself. So as it turns out, the new root is p left, but have we lost p left? That's a good question. Have we lost it? Yeah, I think we might have lost it. So let's make auto left is equal to this, and now we can just do left.p right, and then we can just return left and be pretty sure that we haven't lost it. There we go. That's a pretty safe way to do it, I think. I think this should work. I don't see any terrible problems with it. And then let's do the same thing other than rotate right. So basically, your rotate left and rotate right should be symmetric. So let's try to make this symmetric without breaking anything. We should call this right, and then this is right.p left, and then this should be p right, and then we return right. There we go. So that's it, right? So once you get it done for one of them, you should do it for the other. And that's it. That's really how these rotations should work. So the last thing to do before we go on and maybe run this thing or test it or do something else, is to fix up all of these seg faults that we're bound to get. So the problem here is that what do we need, right? So unfortunately, this is the idea, right? But this code itself, like, this is definitely the correct idea. It's in here. But the unfortunate part about it is that it is just not good because, you know, if you don't test if p left and right and p right, and then you test this, right? So that's how you have to do it. So if this is, so that's one possible thing. Well, what if p left isn't, well, if p left doesn't exist, then you're okay. But the other condition is that maybe p left exists, but p right doesn't exist. So you have to actually check, or something like p left, or sorry, p subroot, root p left exists, and p subroot dot p left dot height is what? Bigger than or equal to 2, I think, right? And the reason why we have to do that, I guess we need to say and not p subroot dot p right. So this is the second condition that we have to put in. So here's the first condition, and then we have a big or statement, and then here's the second condition that we have to look at. So there are two conditions here. Either they both exist and you check their heights, or the left one exists and the right one doesn't exist, right? And so unfortunately you can't just say or p left, because if you do that, then if both of them exist but the heights are balanced, then it'll just check if the left's height is bigger than 2 and ignore the right's height. So that's a problem. Okay, so that's unfortunately the condition that I think you kind of need. Now, there are a million different ways to do this. This is not necessarily, I promise you, this is not the only way to do this. You can split this up into multiple if statements. You can split there's 100 ways that you can attack this problem. But I'm just saying, like, this part here, this is just exactly how I thought to do it in the last 10 seconds, so that's how I did it. So here, if they both exist and the heights are imbalanced, or if the left one exists, the right one doesn't exist, right, and the heights are, this height is bigger than 2, that means that there's 2 children. I guess, let's think. Because, yeah, if the right one doesn't exist, then the height of the left one will be 2, the height of the right one will be 0, so that's an imbalance. So this is correct. Okay, so now we just have to fix. Okay, so now if we get into this statement, we know that p left exists, right? So we know p left exists, and we know that there's an imbalance. So we kind of know that there's a p left like this, but we don't necessarily. Well, actually, we don't. Never mind. We actually don't know if left has a left or a right, unfortunately. So in order to fix this, we have to fix all these like seg faults. So what we have to do is we have to say, if this thing has a left and it has a right, and this happens, right? So that's what you have to say, is that if it has a left and a right, and it has this condition. Because if you don't check for these null pointers, then this will result in a seg fault, or potentially this will result in a seg fault, or both. Okay, so now let's do the other condition where, so what's the other condition? I haven't even said it yet. The other condition is, well, what if they don't exist? Well, we know this thing is left heavy. So if the thing is left heavy, and what would make us in the left case, right? So the thing is, like, if this exists and this one doesn't exist, right? Then we know we're also in the left case, right? Because we don't even have to check the heights anymore, because if I tell you that something has a left child and that left child has a left child, but it doesn't have a right child. So you know that basically what you end up with is something like this, where you have this, it has a left child, and it has a left child of the left child, but it doesn't. This one isn't here, right? No to this. So if that's the case, then you know that you're in a left-left condition. So that's why I'm saying if the subroot.pleft.pleft and it doesn't exist on pleft.prawrite, then this is also a left-left condition. Cool. I mean, these if statements are horrible, right? So the way to explain it is, like, either they both exist and you just check heights as usual, or the left one exists and the right one doesn't. Right, now I guess you could actually factor out the this thing, and there's a bunch of different. I think that is one simplification that you could do, but I'm not going to do that because I don't feel like doing it. So now let's say, well, how do we know if we're in a right case? I guess we're just not in a left-left case, right? We have an imbalance that's not this, so I guess the else is still okay. All right, so we still have two if statements to fix. Here they are, right? So else if, and then we have to do basically all of this, right? We have to do p subroot dot right and p subroot dot left and this, right? So we have to do all of that, and that'll ensure that they both exist, or maybe they don't exist. And so we just say, in this case, we're actually not looking for the we're not looking for the what are we looking for? Oh, we're just checking if it's right heavy. So that's fine, right? If they both exist and the heights are bigger, or if the right one exists and the left one doesn't exist, and the height of the right one is bigger than or equal to 2. Right? Correct? Yes, I think. So basically it's the same thing. Maybe there's a smarter way to do this. But I'm not doing it that way. I'm like splitting up this if statement into a bunch of different parts so that it's kind of more readable, but and then here, same business. We have to check. We know that p right exists at least, but we don't know if the p right has children. If p right has children, then we can do this. Otherwise, what do we have to do? So what's the possibility that's going to fail? Well, actually, so how do we get into the right-left case? We get into the right-left case when let's see, how do we get into the right-left case? We get into the right-left case when the thing exists on the right and then on the left. So basically what we would say is that maybe p subroot dot right dot left exists and p subroot dot right doesn't exist, and then in that case we know that the height of the left has to be bigger than the height of the right because the right doesn't exist. So that would put us into the right-left case, and there we go. Otherwise we do this. So that is basically that for AVL trees. We've done it. We've done it, I think, right? Yep. Let me see if I can steal the display method. I think I have a display subtree method here. Steal that from my binary search tree implementation. Okay, so let's fix up all the problems here. AVL tree node, cout doesn't exist, so let's include IOStream. And using that namespace, std. Okay. I think that's it, really. So let's see whether this... And I think the only thing left is here we have to do value. So, I called it display helper. And now let's copy and paste. And then I think all we have to do... Let's just say, have I implemented display? I have not. Display is just going to call display helper on the m root. We'll make this false, depth 0. There we go. So I think that's good enough. I think we can make our little program now. Let's see if I have a main in here somewhere. BST driver. Let's steal this and make the AVL driver. And we're almost done, and then we can move on to red-black trees. So let's make a void AVL driver. And then let's steal the code here. There we are. I guess we don't really care if we don't care about find. We don't have a find. All we have is an insert and a display. And so we can call this BST because I don't care. We'll just call it AVL tree BST. There we go. And then we don't even have to type display. Let's just always display. And that's it. We just, you know what? Yeah, that's fine. That's fine. Mega simple, right? This is like the most bare bones AVL tree implementation that I think I've done. But it's good because, you know. Okay. It has almost nothing in it. So, okay, so let's call the AVL tree driver, and I'm just curious if this thing is even going to run or compile. Probably not, right? 95% of the time, things will explode. Good. Display subtree. Oh my god. That's funny. Display helper. That's funny. I like that. Okay. Alright, anything else? Who knows? Let's try again. Build project, maybe? See what happens. It built. That's terrifying. Let's run it. Let's insert 5. Okay. We inserted 5. Let's insert 10. Okay. Now let's insert 15. This should get us a right condition. Wow. Look at that. Look at that. Our first imbalance, right? So the thing that it did, maybe we should actually have it print out what it's doing. But clearly what it did, right? So it inserted 15, 5, 10, and then 15 popped over here. And then what it did was it did a, a left rotation. Really, left means up. So it did an up rotation in this case, right? Okay, let's insert 25. It won't do anything in that case. There we go. Now let's insert, say, 12. There we go. Now let's insert, I don't know, insert 30 or insert 18. Let's see, what will 18 do? 18 will have a height of 1, then this will be height 2, this will be height 3, this is still height 1. So it's going to be a, here it's going to do a zigzag, right? If we put the 18 in, it'll put it in here, but what it's really going to do is it's going to do a zigzag on 10. So it's going to rotate 12 up here, and then it's going to rotate 12 up again. So it's going to, I think that's what it's going to do. Let's see if I'm right. It's a little bit hard to read this on the side, so maybe I'm wrong. Let's just hope I'm right. I'm wrong. What did it do? What did it do? What did it do? It didn't do anything. Okay, why didn't it do anything? That's a good question. So this is height 1, this is height 1 and 2, this is height 3, this has height 1, so it should have done something, right? It should have rotated. There's a bug. Let's insert 40 and see what it does. Insert 50. Oh, well it did something there. Huh. But, yeah. I think was there a bug here, or am I just crazy? So let's pull up the visualization and see what happens. Let's reset the tree. Is there a way to reset? I guess you just refresh. Okay, so what did I do here? I inserted 5. I inserted 10. Let's just and then I inserted 15. Whoops, 16. Whatever. And then I inserted right, so that's good. And then I inserted I guess 25 and 12. Okay, and now I inserted 18. So let's see what happens here. Or maybe it could be that I'm just wrong about what should happen, but I don't think I'm wrong, because if you notice here, there's actually an imbalance when you get up to 10. So it should rotate. Oh, I guess it's actually a right rotation. So this should actually just, it shouldn't have done a zigzag. It should have just rotated 16 up. Like this. But it didn't do that. It did not do that. So I guess we can debug a little bit. So our rotations seem to work. We don't lose nodes. So how can you tell? This is a good rule of thumb. It's like, how can you tell if your rotations work? The answer is generally if the shape is right and you don't lose nodes, right? So sometimes if you don't set the pointers correctly, if you do something weird, nodes can just vanish if you don't do the rotations correctly, right? Because basically what you're doing is you're chopping off a bunch of pointers and you're setting them to new pointers. So it's totally possible. If you like lose part of a subtree, check your rotations, right? Because that's where a lot of this is being done. I mean, not all of it, but definitely this is the first place to go. And then, so why didn't it detect the case here? Good question. Good question. Did I do something wrong? I mean, the answer is obviously yes, but what did I do wrong? It didn't detect. The problem is that it didn't detect a right case. So why would it not have detected a right case? The answer is that those are both non-null, so it would have executed this part of the statement, and then it would have said if this height is bigger than this height plus 1, which would make it a right. This makes it a right case. So let's just see out right case, and then here, let's check this out. So I think I did this one the fastest, so this one might be wrong. I guess that would make sense, right? Oh wait, but that's not it. We want this to be, we know it's a right imbalance, and we want this to be false. So so it's not going to be this, because right was a node, so it's going to be in here. And so if p right.p left and p right.p right, so that will be the correct one. And then if the left, no, I think that's right. I think that's correct. This is right left dot height is bigger than or equal to the right dot height. Yep. So why didn't it execute that rotation? Whoops. Sploops. What have I done? Where have I gone? Okay. So let's do this again, and I mean it's not a terrible waste of time just to show some debugging. We'll go on to red black if I can't get this in the next few minutes. I'll probably fix it up after class. Okay. Oh wait, insert 5, insert 10, insert 15. I forgot about the insert. Insert I think I made it like 25, right? And then I inserted 18, and then I right case, right, left. So what happened here? Why is this not displaying correctly? Or what happened to this tree? So the 10 and the 5 are okay. Oh. Am I just dumb here? Yeah, I'm just dumb. Never mind. Never mind. This is correct. This is not a bug, right? Inserting the 18 is going to cause... Yeah, that's exactly right. It's going to cause a right-left case, right? Because it goes right and then left. And so it will cause a right-left case, which does cause this rotation, which does... This is all right. Okay. Let's try insert 30. So this is the case where we have a right-right. See, this is the case where it's not detecting. It's not even detecting that it has an imbalance. So it's not detecting the right case. That's a good... So you see here, the way I know it's not detecting the case is it's not telling me that it's a right case. It's just not saying anything. So that's how I know that this is somehow wrong. So it was doing the rotations correctly. It's just not doing the right. It's not detecting the right case, which possibly also means the left case too has an error with it. But I'm just testing out the right one. I guess the last thing to do before we move on is just to ask: is there anything obvious here that's wrong? P subroot .p right .height is bigger than P subroot .p left .height plus 1. You subtract, and that means that right height minus left height is bigger than 1. That means there's an imbalance. Interesting. Oh, I wonder if it's actually... No, it shouldn't be. That shouldn't be a problem. I think one thing we could do to fix... I'm not sure if this is a problem, but we could always just take this code and put it here. I'm not 100% sure. If that will... I don't think that's going to fix anything. It will... It does shorten the code, but I don't think it fixes anything. Because at every level of the recursion, it's going to... So here it's going to return. So then we're going to do this. We'll refresh the heights on the current. We rebalance the current. And then we refresh the heights again. Oh, I know what the problem is. We have to refresh the heights after every rotation. So that's... I know what the problem is now. The other thing that we should have done, and this is a bit of a hint to you, is that we should really be displaying the heights, which I'm not doing. Notice how I am not doing that here. So let's display the heights so that we know so we're going to have everything is now an ordered pair where the first entry is the value and the second entry is the height. And let me see if I can get this to work now. So let's insert 5, insert 10, insert 15, right? Cool. Insert 25, insert 30, right? Oh, that actually did rebalance. But notice what's happening here. The heights are wrong because I didn't refresh the heights after every rotation. So let's fix that. And what do I mean by that? What I mean by that is that if you do a like a left-right rotation or something like that, you have to... Actually, I think the safe way to do it would just be to... on right. Let's see if this fixes it. I think this is probably the safer bet. I know I'm going to be doing it a bunch of extra times, but it shouldn't matter as long as it's correct. There we go. So heights are still wrong. Notice how here the height is 1, that's correct. But here the height is 4, and here the height is 3. So, right, what do we need to do? We need to refresh the heights on the right dot. I think it's right dot left. And then here we need to refresh the heights on left dot. Like this. Okay. See, I'm remembering how to do this. I've forgotten all the little details. There we go. Now you see. Now you see. And of course you ask, well, what do I see? I see that the heights are 1 and 1 and 2. So now the heights are correct. Let's see if inserting 20, insert 25. So you see here how this height is 2, this height is 3, this height is 1. All the heights are now correct. So I think if we insert, say, 18, what happened? Oh God, what happened when I did that? So that was a complicated one. So it inserted 18 here. Right, it went to the right of 10, to the left of 20, and to the right of 15. And so we had a, in this case, we have a, well, we don't find the imbalance here, we find the imbalance here. And so we see a left-right imbalance, or I'm sorry, a right-left imbalance, right-left imbalance. Oh, I mean, it's even telling me what it's doing, so I should just read my own code. So what is it doing? It's going to rotate, it's basically going to rotate the 15 up, and then it's going to rotate the 15 up again. So it's going to rotate the 15 right, and then it's going to rotate the 15 left. So did it do that? And the answer is, I mean, the answer is yes, actually, but let's just look at it and make sure. So which order of insertions did I do? Let's do it again with this tree, just to prove that it actually worked. So let's insert 5, 10, 15. I keep doing that. 16. Doesn't matter as long as everything else is right. I think I inserted 20 then, and then I inserted 25. Right? Didn't I? I inserted 25. There we go. And now I insert 18. And let's see what happens when we insert 18. So there we go. It updates this height. It's 2 now. Updates this height. 3 now. This is not where we detect the problem, right? Because where here we have a height of 3. We can't actually see over here yet. What we do see is that here, let me just blow this up just a little bit. So what we do see is that this has a height of 2, this has a height of 1, and so overall, the issue is, well, I should say overall there's no issue here. Let's go to the next step. Here there's an issue. Height 1, height 3. So it tracks down through the maximum heights. It says the height is biggest on the right, the height is biggest on the right left. And so what it's going to do is it's going to say, aha, and it says double rotate left, which is not exactly, I mean, it's some mixture of rotations, right? So what we're going to actually do is rotate the 16 up and then rotate the 16 up again. So there we go. And now does that match here? Other than the fact that this is 15, it does. Cool. So, all right. So that's an AVL tree basically implemented. And I think we can kind of, once we do these refreshes, I think we can get rid of some of the other refreshes. But I would have to check that out before I think what we can do is get rid of these refreshes now, because we're refreshing after the rotations. So actually, now look at this insert helper code. This is I think this is kind of beautiful actually. This code is pretty nice. On the other hand, this code is kind of ugly, but it is what it is. You can kind of just ignore it. The rebalance code is grotesque, of course, and the rotations are okay. I think the rotations are fine. They get a little bit uglier if you have to track parent pointers, because if you have a parent pointer, the problem is that you always have to check. The point is, if you have a parent, let me just say this. If you have a parent, you always have to check whether a node is the parent's right or the parent's left. And then you have to do something like node.parent.right is equal to something new, or node.parent.left is equal to something below, right? And so that it generates a lot more statements inside of these rotations, but the good news is that we don't have this. Okay, so now with the last 18, 20 minutes of class or whatever, I'd like to start talking about, I will post this to the GitHub. Some of this you can probably use, but don't just copy paste this, because that would be bad. Just use this to learn. It's obviously the project requires you to do more than this on an AVL tree. But the point is, the rotation code, I think rotation code will exist essentially anywhere. If you look this up in textbooks, you'll be able to find essentially this code. So there's no reason for me not to just give you some of this code. This is grotesque. Please don't reproduce this. Find a better way to do it. Actually think through the problem, unlike me, and do it better. So, okay. All right. So I think the rest of the day we will just do some theory, right? Let's talk about theory. So this was all application, right? And this feels very applied. You see a lot of code. It's all kind of grotesque. Well, some of it is. Some of it's beautiful. Some of it's okay. It's a mixture. But now let's talk about red-black trees. Okay? So let me go to the top of that. I have to steal the red-black properties. I never bother to memorize them, so you can blame me for that, I guess. Okay, so let's talk about the red-black properties. There's 5 rules to be a red-black tree. So the 0 rule, which is not actually usually listed, is that the tree has to be a binary search tree. So your tree is a binary search tree. Okay? All right. Now that rule 0 is out of the way, let's talk about rule 1. Rule 1 is that every node is either red or black. Okay? So what we do, the idea of a red-black tree here is it comes from the question is okay, AVL is great. Makes us happy. But are there other mechanisms that we can invent that balance out trees that aren't dependent? And the answer is yes. And so we get into red-black. And so the issue about red-black is that the cool thing, so with red-black, we don't track heights. Nodes, so in an AVL tree, right, each node knows exactly how high it is, right? It doesn't necessarily know how tall the tree is totally, but it knows how high it is in the tree. In a red-black tree, all you have is a single bit. Now, normally you have to store it as a byte or some kind of thing like that, so you can't just store it as a single bit. But in some of the algorithms language, they'll say all you need is 1 bit of storage. Of course, you can't allocate 1 bit of storage, but that's not the point. A single bit, which is either 0 or 1, and one of these is red or black, right? So that's all you really need, right? Is red or black. And now, if I just tell you a color, a color doesn't tell you the height, right? So that's pretty clear. Color doesn't tell you very much about the structure of the tree. All it tells you is a color, right? And you might be thinking, what does this color do? And we're about to get to that. So every node is either red or black. There's no gray nodes, there's no green nodes, there's no in-between nodes. So every node has exactly one color. It's either red or black. Rule 2 is that the root is black. Okay? This is kind of, I mean, yeah, the root is black. Let's not even talk about this rule. It's a pretty simple rule. There's a reason for this rule, but let's not even talk about that reason until we draw out some red-black trees. Every leaf, so what they mean by a leaf in this case is a null pointer is considered black. But this only, okay, so it kind of matters. Most of the time it doesn't matter, but it's a rule. It's a way to make sense of certain shapes, where if you have like basically it's like if you have the condition that I actually just deleted. So if you have like the right-left condition here, and let's say that this node is black because it's the root, let's say this node is red because it's a node, and then let's say that this is black. And then your question is, okay, so, what happens in this case? And the answer is, well, nothing really happens. Well, actually, you do have to do a rotation in this case, but let's not pay attention. I'm not talking about insertion yet. I'm just talking about structure. So you have a null pointer sitting here. And you have an arrow that goes from this red node to this null pointer. And the question is, what is the color of this null pointer? And so the answer is that the color of this null pointer is black. Okay? So null pointers are black. That's what they really mean here. So I really should just say every null pointer. A lot of books will say every leaf, but only in the case where you actually think null pointers are leaves, which I tend to not believe that very much. So let's actually say that just every null pointer is black. Every empty is black. Okay. And so this one is, it's an important rule, but it's not like the most important rule. And this is the most important rule. If a node is red, then both of its children are black. And so you might say, well, what if it doesn't have two children? And that's where we go back to rule 3, where null pointers are considered black. So a red node can have two null pointers sitting out from it. But why is this, why is this... So rule 1 and rule 2 are just kind of, rule 1 and 2 and 3, they're kind of like, okay, that's just setting up the rule of the game. Rule 4 is the one that actually determines a lot of the behavior of a red-black tree, okay? And so why do I say that is basically the most important rule to remember? That if a node is red, then both of its children are black. And the reason why it's the most important rule is because, I'll say rule 4a, which is we always insert red nodes, okay? All right. And so how does that determine the structure of the tree? Well, basically rule 4 works together with rule 5. And here's rule 5. For every node, the paths from that node down the tree to a leaf null pointer always or must have the same black height, not black height. And so what is black height? Well, let's talk about it. So here is a tree. Whoops. Oops. Okay, so this is not a red-black tree, actually. And you might be like, well, why? And the answer is, well, it follows rule 1, red, black, red, or black, red, black. All the nodes are one or the other color. The root is black, yep. Every null pointer is black, who cares? If a node is red, its children are black, yep. But what about rule 5? do all of the nodes have the same black height? And so the question is, what is the black height of the root? And the answer is, let's see, right? So either the black height is, if you go down this way, let's just say that the black height here is 0, so BH is equal to 0 at this null pointer, so maybe the black height is 1, but the black height is really, if you measure it the same way, so like black height of x is equal to 1 plus, or really it's, if the node is black, then it's 1 plus the, the max of the black height of the x dot left and black height of x dot right. Right, so here's the thing. We go down this way, the black height is, say, 0 this way, but the black height is 1 this way, right, because we have a black node here. So the black height is not the same in both directions. Black height here is equal to 1. The black height at this red node is also equal to 1. And then the black height here is equal to, well, it's either, on this side, it's since this node is black, it's 1 plus 0 or 1 plus 1. So actually it's the max, so it would be 2. But here you notice that there's a problem, because the black height on this side, it doesn't match up with the black height on this side. So this doesn't, since this doesn't match, this is a problem. Okay? Now, you notice that the node only has a color, so it doesn't actually keep track of the black heights. So you might be wondering, like, how on earth are we going to actually track all this and make sure that things work? And the answer is you have to be... let me show you an example of a red-black tree that is a red-black tree. So here is one that is, right? So here is a red-black tree that is a red-black tree. Here we go. And then this one will have these 4 children nodes. So here's one. This is a red-black tree if you fill in all the arrows. Here's another example of a red-black tree. So there's one. And you might ask yourself, well, like, that doesn't look very balanced, right? Now, actually, as it turns out, that's an AVL tree as well as a red-black tree. But you can create some more unbalanced conditions. So for instance, you can do something like this. You can put 2 black nodes on this, and then you can put, say, 4 red nodes as these children here. And then, of course, you can maybe even put even more black nodes as their children. Well, can you do that? Let's see. What? Yes, you have to. So this is the right side, and this is the left side. And so now we do something like this, where we're starting to... The problem is that as the tree grows exponentially, the amount of space you have decreases exponentially. So the nodes are just going to kind of blob into each other. But just ignore that for the moment and pretend that everything's good. So this is also a red-black tree. And so you might say, well, this is definitely not an AVL tree, right? And it isn't, I agree. But why is it a red-black tree? And the answer is, well, all the nodes are red or black. The root is black. So all of that's correct. What's the other rules for a red-black tree? The other rule is that every red node only has black children. Red, black, black, red, black, black, red, black. All of the reds have black children. None of them have red children, so that's good. So rule 4 is satisfied. And then the most important rule is the black height rule, which says that the black height has to be the same. So you look at the black height of all the different nodes technically, but really let's just look at the root. You notice here that the black height here is 1, 2, 1, 2, 1, or I'm sorry. I guess technically you say the black height is 3, so this is like 1, 2, 3, 1, 2, 3. Here it's 1, 1, right, because the red node doesn't count. So 1, 1, 2, 2, 3, 1, 1, 2, 2, 3, 1, 1, 2, 2, 3, right? So all of the red nodes, they don't count for black height. Therefore, they are, So the black height of this tree is constant, right? On both sides. Or what should I say? Not constant. It's the black height of this tree is invariant along all paths is technically the right way to say it, but you get what I'm trying to get at here. The black height is the same regardless of which way you ask the question, right? So that's why that works. Okay, so basically those are the 5 rules, technically 6 rules, like, and the 6 rules plus this thing, we always insert red nodes. And so let me show you why inserting red nodes is good. Okay, so let's just say that we start out with this little tree here. You know, a nice little red-black tree going on. So if I inserted a black node, right? The reason, so, okay, let me just put it this way. Why do we insert as red? The answer is, the rule says we can have black children if black, but red can't have red children, right? So black can have black children, black can have red children, but red can't have red children. Red can only black. So the issue here is that because the red children can only have red cannot have any red children, then what we're doing is we're actually trying to cause a problem with Rule 4. Right? We're trying to cause a problem with Rule 4, and the reason why we're trying to cause a problem with Rule 4 is that will force us to rebalance. Okay, so that's what triggers the rebalancing operation. Because if you notice, if we just inserted everything as black into this tree, so we insert, say, a node here, then we insert, say, a node here, then we insert, say, a node here, the point is that unless you then scan all the different, like if you didn't do something like this, and then like scan all the black heights, you wouldn't know that in fact this thing was just complete garbage, right? Because this doesn't violate any of the rules that you can tell. The secret is that we never actually check this rule. So the algorithms enforce this rule. We don't check it. And so if we were inserting black nodes and we didn't check all the black heights, then we would just end up with a regular binary search tree, and we wouldn't be able to tell if there was an imbalance because, as I say, the black nodes are permitted to have black children, they're permitted to have red children, so it doesn't matter what's going on. So that's the problem. So, but what happens if you try to insert a red node? Let's say the red node inserts right here. Aha, violation of Rule 4, right? Rule 4. Let me close that. Okay, yeah. Rule 4 violation. And that's it's a good thing, okay? It's a good thing that it is a violation. And the reason why it's a good thing that it's a violation is because it tells us that we have to do a rotation, okay? And so basically, the trick here is the trick is that we always ask about the uncle. And so here the uncle is red. So in this case, you actually don't have to do a rotation. You just do a recoloring. And then you do this recoloring, like this. And then you just recolor the root. So now this went from a rule violation, right, to a red-black tree again. Because if we just change the color of these two to black, then we're good. And then we're happy. Okay. So there are other cases where if this node is black, then there's other things that you have to do, and that actually triggers a lot of the rotations. But if the uncle is red, then this just triggers a recoloring. So anyway, I think that's basically it. I think that this is good because I've started on the theory of red-black trees. So next time what I can do is I can launch right into all of the annoying rules, basically the uncle rules. So if you're curious about like for instance, how the heck do we know what to do given these colors, right? Right now they're kind of magical. You know, mostly just kind of random. And the answer to that is yes, they are. But I will show you that there are rules. There are 3 insertion cases that basically what they do is in one case you recolor, and in the other 2 cases you do some rotations and recolorings. So the other two cases are more complicated. But the point is that there are 3 insertion cases. 1 case is a recoloring case, 2 cases are rotation cases. And after that, what I'm going to show you is, and then we'll argue this, we'll actually draw it out and prove that the heights, the black heights, are correct after these recolorings rotations. Because it could be that you do a rotation and it could completely screw up all the black heights. It could mess everything up, right? So what you have to do is you have to prove that it actually works. And so we will do that next time. So we'll do the 3 insertion cases, and then we'll prove that the black height is correct after the the black height is maintained after the rotations and the recolorings. And the last thing that we're probably going to do is we'll prove kind of the standard fact about red-black trees, which is that the number of nodes is I guess at most 2 to the like black height of x plus, or something like that. It's 2 to the black height, I think, plus 1 minus 1, something like that. I'll have to actually check and make sure that I'm right about that, but the point is that yes, the whole point of this fact, and the idea here, and the point of this fact, is to show that given a certain black height, the total tree height is limited, and the number of nodes is logarithmic. Or I guess exponential in height. So the search time is logarithmic, right? Because the point is that if the number of nodes is exponential in height, then what that means is that there's no linked list structure going on. We are making sure that at every level there's a lot of nodes happening, so that we can maintain the log x or the log n search time, right? Basically, that's the whole point of AVL trees and red-black trees, is that a binary search tree has the O of n worst cases, but AVL and red-black do not have O of n worst cases for insert, find, delete, right? They are limited to O of log n, and remember how much better that log n is than O of n. So that's the point here, is that log n, so if you have 1,000 nodes, right, O of n is some constant times 1,000, but then log n would be some constant times 3, right? If we're taking, I guess if we're taking log base 10, or log base 2 would be something like 10. And if you have, say, 1,000,000 elements, then that's C times 1,000,000 is your runtime. And in the other case, it would be C times, 20. Right? So 20 steps is way better than 1,000,000 steps. And so that's why these weird constructions of AVL and red-black are done. It's because it adds a lot of complexity to the code. You do have to test everything out. Everything needs to be actually done really carefully. But the advantage is that you can run it and it will go way faster, and so you can do calculations or computations that you wouldn't have been able to do otherwise. All right, so that's really everything for today. I think that, so this is pretty good. I think we've gone over all the rules for red-black, so that's it. Okay, and then we implemented AVL. So I guess I need to upload some PDFs and the code, the AVL code. Or maybe I won't upload the AVL code. You can actually just read it on my screen if you're curious. That way we can prevent any urges to just copy paste any of it. Because I know that the issue is that there's an AVL tree project, but I really didn't want to leave you guys completely stranded without any AVL help. All right, so that's it for now. I will let you all go. if I can find OBS. There it is. All right, goodbye.